Well, welcome. So today I'm going to have another look at the fast mission that I did last week. The weather's not great today, so I'm not going to be able to fly anything, but having a look at the logs is going to inform what I do next and be able to see some of the things that I'm looking for. So I've got the log here, as you can see in the window, and if you remember, I could just bring up the map just so you can see. I did this mission where I'm flying essentially a square pattern, waypoint, takeoff, waypoint, 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 back to home. And now the interesting thing about this is the these settings, these log settings, PSC. So this is PSC stands for the position controller, and these are there's this position controller in the down, the east, and the north direction. So this Earth frame, down, east, north. And unfortunately, there's not a body frame orientation for these, so you can't see how these look with reference to the copter itself. And so what Leonard says is that typically if you're doing some testing in this area, that you should fly north, south, or east, west, so that these reflect easier to use coordinates. Now, if just go back to the map again, you can see sort of north, south. So you can see that east, west gives me a reasonable approximation for something in a straight line. Not quite, but good enough, at least for this first segment. So I'm going to look at the east-west component. Okay, so what we've got here is the target position, the actual position, desired velocity, target velocity, actual velocity, desired acceleration, target acceleration, actual acceleration. So if I look first at the target position and the actual position, and our first waypoint is sort of, I think, probably here, where we change the position starts changing. And you can see that the positions track fairly closely, so that's good. So it means we're actually going in the right direction. But if we look here, target versus actual position, there's still a fairly significant deviation of about a meter. So this is in meters. So our actual position is about a meter behind where we want to be target-wise, and I'll come back to that in a second. But if we scale this back up, so this is the. Let's do that. So this is target position, actual position. So then if we look at the target velocity and the actual velocity, so you can see here that again there's some discrepancy between target velocity and actual velocity, which gets quite large, and so you can imagine that the velocity is increasing, the copter is speeding up, and then it's starting to slow down again as it reaches the waypoint. So we're trying to not quite stop, but slow down in time to reach the waypoint. And you can see at the sort of maximum speed part, the target velocity is fairly far behind the actual velocity is fairly far behind the actual velocity, a bit behind the target velocity, 2 meters a second, and so the copter is not getting up to the target velocity, and also it's fairly far behind my maximum. So my maximum is set to 30 meters a second, and you can see that we never get anywhere close to that. So to understand why, you have to look a little bit deeper, and so we can sort of pull up the target acceleration and, oops, the actual acceleration. So here we've got target acceleration, actual acceleration. So if we just look at this up to the first waypoint again, so this is kind of the first waypoint here. And you can see that the acceleration increases quite rapidly and then decreases as the velocity levels off. And one thing to note here is that the jerk setting, which is the rate of change of acceleration, is this slope here. So my target acceleration gets all the way up to about 15 meters per second. And my jerk, if we have a look at the values, so here is, this is 11:05:17, 11:05:19, so roughly 2 seconds to get from 0 to 15 meters per second, which means my jerk is about 7.5 meters per second. But I actually have jerk set to 10, so I'm not actually achieving my jerk setting either. So what is going on? Well, to understand what is going on, so I'm not achieving jerk, I'm not achieving acceleration, my maximum acceleration is 20. I'm not even achieving velocity, which is set to 30. And my position is trailing. So although in the video that you saw from last time it was quite a fast mission, I'm not getting anywhere close to what I actually want. And clearly there's room for improvement here. And so there's a couple of things going on here. So the first is based on the settings that I've set, there's not enough room, not enough space to get up to maximum velocity or even maximum acceleration. So for instance, if my first waypoint was 500 meters out, then these would keep increasing until I got to my maximums. So both maximum velocity and maximum acceleration. So one of the problems is that based on the settings I have, there's just simply not enough distance and therefore not enough time to get to the maximums. So why is this? Well, what you've got to remember is that in any control system, what you're operating on is the error. So the action of P in a control system is proportional to the error. The action of D is proportional to the derivative of the error, and so it's the magnitude of the error that determines the magnitude of the input. So what is the error in this case? Well, in this case the error is essentially in relation to the lean angle of the copter. So if I have a look at the easterly PID, and in particular look at the I term, let's see if we can get this a bit better. Okay, there. So what you see is, so what happens is, this is all based off the error. So the copter is not where it needs to be. It's not going as fast as it needs to be. It's not accelerating as it needs to be. What is the error that's telling that affects the control systems that tells us those things? And essentially it's the lean angle of the copter. And so what happens is that the I term, which kind of represents the long-term control input to sort of, so the I term is the integral of the error, but this is what you need to maintain a particular condition for some period of time. So in our case, this is what we need to maintain a lean angle and therefore go fast forward for some period of time. And you can see that this I term takes some time to build up. And it's because of the time that it takes this I term to build up that these values are not getting to their maximum. Now, there's something else quite subtle going on here, which is that not only is the I-term taking time to build up, which means the response is slower, but we also don't want these errors to get too big. And so the control system makes that happen by slowing down time, if you like. So essentially, if these operated to the maximums that we've set, then the errors would be much larger, and we have no hope of actually making those errors up. It's not actually going to get any larger. So instead, the control system slows down times to make the magnitude of the error not too big. Now, so what I could do is I could increase. So some of the things I've considered here is, okay, so we've got this acceleration here. Maybe I could increase jerk to make this acceleration more rapid. But the problem with that is that the I-term buildup will still be at the same rate, and so it's likely that even if I increase the jerk, the graph will not look any different. So the I-term buildup will just be at the same rate based on the error, because the error will essentially be the same. So what I actually need to do is I need to set the feed forward component, and so there is a parameter which is called PSC underscore vel xy underscore feed ff for feed forward, and this is a way of directly affecting, effectively directly bypassing this I-term buildup. So instead of relying on the error to produce the output that you want, you instead provide a feed forward term which says that you basically know something about the relationship between the response that you want and the input. And in this case, PSC vel xy ff is the position controller xy component feed forward. And what we want to set that to is essentially acceleration divided by velocity. And so that gives the relationship between acceleration and velocity, which allows us to reach the lean angle that we need to support the acceleration that we want instantaneously, effectively. And so in order to do that, I'm going to have to measure it. I'm going to have to measure what feed forward component I need. And so the way I can do this is measure the constant acceleration portion relative to the speed portion of a run. So what I'm going to do, this graph is not suitable for it because it's not facing north, south or east west, and there's not enough time and distance to build up to the required maximum. So what I'm going to do is when I next get some weather, is I'm going to go out, set up facing north-south, and just do a single mission where basically I go out to a few hundred meters and then hit RTL. And RTL will accelerate the copter as fast as it is able to, based on the settings I've set. And what I'll be able to see from the acceleration I get and the velocity that I get, what is the relationship between those two in terms of determining the feed forward that I need. And then and this is a proportional relationship, so it should be that greater acceleration requires proportionately greater feed forward. And so the relationship should hold as long as the velocity and the acceleration are constant. The relationship should hold. And so what I'll do is I'll set that up, input the feed forward component, and then I should be able to raise, in particular I should be able to raise the jerk much higher to get a much more rapid acceleration to the waypoint. And so what I'll be looking for is setting jerk higher, and Leonard says jerk needs to be equal or maybe even double the desired acceleration. So my desired acceleration at the moment is 20 meters a second, so I'm going to set the jerk to maybe 40 meters per 20 meters per second. Set jerk to 40 meters per second, and then we'll see how I get on with that. And what I should be able to observe is essentially no build-up in this item, because the error component of the lean angle is being directly applied by the position controller rather than requiring build-up of the item. So I should be able to see a much flatter item component, much better response, and therefore a much faster mission even over these short periods. So that's the theory. I need some good weather to try it out, but it's sort of an interesting area, and I think what I plan to do is see how hard I can push this. So obviously I've got my sort of waypoint limits set that relate to aspects of the position controller. I also have the angle limit set, which is essentially the maximum, it determines the maximum acceleration that I can achieve. So if you think about the angle of the copter, it's the forward component of the force that gives acceleration. So since the position controller will keep the height level, there is the force at a particular angle will be fixed, and therefore the acceleration at a particular angle will be fixed. So if I'm up like this, then I get a very large force in the horizontal component and a very large acceleration. If I'm down like this, much lower force, much lower acceleration. So those are the things I'm looking for, and we'll see how that goes. Thank you for watching. Bye.